for section 3.3, free fall. Free fall is a special case of uniform acceleration or non-uniform motion. It's the case when you're just falling under the force of gravity. We're going to make things simple in this course. We're not going to talk about air drag. We're just going to consider objects that are acted on by gravity alone. And what Galileo discovered some 400 years ago is that if you disregard air drag, all objects, heavy and light objects, all have the same acceleration when they're pulled down by gravity. That acceleration turns out to be 9.8 meters per second every second. So when you drop something, it speeds up 9.8 meters per second for each second it's falling downwards. Remember, acceleration is a vector, so it has both a size, the 9.8 meters per second squared, and a direction. The Earth always pulls downwards. You should watch, because we on the Earth always think that light things have a different acceleration than heavy things because we see air drag. But in 1971, they took a hammer and a feather to the moon and dropped them where there's no air, and the feather hit the ground at the same time as the hammer. A classic way to visualize free fall is a picture of something being dropped. So here we have essentially a motion dot diagram, because the ball is the dot. And what you can see is when you drop something, it falls further and further each second. You should be able to recognize now by looking at that that means it's speeding up. Well, clearly it's falling downwards, which means the velocity is down. And we just said that acceleration is 9.8 meters per second down. So when you drop something, the acceleration and velocity vectors are both in the same direction, and it speeds up. This picture, if we changed it a little bit, we could also put the hand down here, and this would be the same picture you'd see if you tossed a ball upwards. If you toss the ball upwards, I hope you can envision in your mind that it slows down, and the dots would get closer together. Well, in that case, the velocity is up. Acceleration due to gravity is always down. So velocity and acceleration on the way up are in opposite directions, and the ball slows down. So our simple rules about the directions of velocity and acceleration hold for free fall. Now let's look a little bit more carefully at the velocity time graph, and in a minute the position time graph for an object as you throw it up in the air and it comes down. Here's the velocity time graph. I guess the first thing to note is that it's a straight line with a negative slope. Well, what does the slope of a velocity time graph mean? Well, it's acceleration. And acceleration is 9.8 meters per second down, or negative. So the slope of this line is minus 9.8 meters per second. The next thing you'll notice is, well, what's happening? First, it starts off going fast, and then it slows down. Which way is it going when it starts off fast and slows down? Well, that's when you toss it up in the air, and as it goes up, it slows down. And notice what happens at the very top. At the very top, the speed goes to 0. Does that make sense? The instantaneous speed goes to 0 as it changes direction, and then it begins coming down faster and faster and faster, because negative velocity means you're going downwards. And as you go down, you pick up speed. So first, you slow down as you go up. You come to a moment or an instantaneous stop, and then you speed up on the way down. Notice the slope never changed. The acceleration is the slope of this line. The acceleration is coming from the planet Earth, and the slope of this line is a constant negative 9.8. It's negative 9.8 on the way up, negative 9.8 on the way down. the Earth doesn't know anything about the ball. It's always the same acceleration. Now let's look what the position time graph looks like. Maybe a little easier to visualize because when we toss something up in the air, we kind of see it as going up and down like that. Remember, this is over time, so what we really did was toss it straight up in the air, and then it came back down, and we plotted that as a function of time. Well, one thing to notice is that looks like a parabola, and in the last section, we talked about when you have uniform acceleration, position graphs are parabolas. In this case, the acceleration is negative, so we have a down-facing parabola. Look what's happening to the slope. Remember, the slope of a tangent line is the instantaneous velocity. Can you see in your mind's eye that the tangent slope is becoming less and less? It's steep here, less steep, and then right there, right there, it goes to 0. I wonder where that is. Let's see, 2 seconds. Well, let's go back. At 2 seconds, the velocity was 0. And where were we? At the top. At 2 seconds, the slope of the position time graph is 0. And where are we? We're at the top. After that, the slope gets steeper and steeper and steeper. That means the velocity is getting larger and larger and larger. And that makes sense because on the way down, you pick up speed. Let's take a quick look at the self-check, see how we do. Sorry, guys. So, who studied gravity 400 years ago? Galileo Galilei. Even before famous Isaac Newton, Galileo realized he's the guy that dropped things off the Leaning Tower of Pisa, figured out that they have all the same, they hit the ground at the same time from the same distance, so they had the same acceleration. Blank is the motion of a body when air resistance is negligible. That means you don't count it. And only gravity. Well, that's the definition of free fall. Oh, look, here's a position time graph just like we talked about. At what time is the object's velocity 0? Well, you need to remember, how do you find velocity? It's the slope of a displacement time or position time graph. So the velocity is 0 when the slope is 0. Well, the slope is 0 at the tippy top. Just for an instant. First it's going up slowly, then it's 0, then it starts down slowly and picks up speed at the instant at the top at 2 seconds. The ball falls freely from rest for 15 seconds. Okay, well, this is where having the formula sheet so you can look is helpful. I know these formulas well enough. I say to myself, there was a formula for the final velocity equals the initial velocity plus AT. Falling from rest, the initial velocity is 0. So the final velocity is just the acceleration, 9.8, times the time, 15. So it's a little less than 10 times 15. So it's these two. And then which way is the velocity when it's falling, up or down? Well, velocity is the direction you're moving, so it's down. Here's the last question. It's a little bit tricky. It says a 75 kilogram swimmer steps off a 10-meter tall tower. What is the swimmer's speed when they hit the water? Well, one thing to notice is they gave us 75 kilograms. Have you ever seen a problem with mass in it before? No, we haven't talked about mass yet. So this is an example where they gave you extra information you didn't need. You might say, as a student, well, that's stupid. Why do they do that? Well, I'll tell you, as an engineer, it's because in the real world, you don't know what you need to know. That's part of the job, is figuring out what the data you need is and what the data you don't need is. We don't need the 75 kilograms. So how are we going to find the speed? If you look at the equations on your equation sheet or back in section 3.2, there were 3 of them. 2 of them involve time. We don't know the time. So this, in the last screencast, I said this is when you want to use that third equation that has v final squared equals v initial squared plus 2a delta x, because it tells us the speed without knowing the time. To use that formula, the initial velocity is 0 because I stepped off it, not moving. The acceleration is 9.8, and delta x, the acceleration is minus 9.8, and delta x is actually minus 10 meters because they went down 10 meters. So I would say that the acceleration is negative and the change in displacement is negative. The two negatives cancel. If you do the math, try it yourself. You should find, if you remember to take the square root on the final velocity, that the answer is 14. I know this section might be a little tricky. If you have questions, please bring them to class. I would love to help answer them. And I hope this has been helpful to you.